Alright, just so you know, I'm going to give lots of notes in this video. I suggest you write the factual information in that grid area on your note-taking sheet, and then anytime I do an example, flip to the back of the page and do the example there just to save some space. There's going to be about 4 or 5 examples in tonight's video, so you need space for 4 or 5 examples on the back, and then keep all the factual information, so definitions I give, that kind of thing, on the front. Alright, tonight's video is all about vectors, and I want to start out with 2 important facts that you should have gotten out of the reading. If not, I'm highlighting them here. First, a scalar is a number with units. So anything that's 3 meters, 2 meters per second, what you've generally been dealing with, number with units. Vectors are quantities with magnitudes and directions, and we've talked about this before. So a number with units and a direction. Like when the plane was landing, we talked about whether the acceleration should be negative north or negative south or positive north or positive south. The direction was the important part that made it a vector. Alright, so let's set up a little problem in real life where you can see how vectors are useful. Suppose that you're right here on a map, and someone says, let's go to the library, meet me there at 3 p.m., it's half a mile away. Well, that's not really helpful. The library could be half a mile this way, or half a mile this way, or half a mile this way. What if this one's the real library? Well, the person who said half a mile should have said half a mile north-west. Then you'd know the library was this way. So a vector is important because it tells you the direction, not just the distance. You could have gone half a mile any direction. Same thing. Also, even if you know where the library is, there might be stuff in your way where you can't walk in a straight line. So like we talked about, I think the first day, there's a difference between distance and displacement. So let's say to get to the library I have to walk a little bit west, then a little bit north. Well, so however long those 2 parts of my trip were, this part plus this part, that's my distance. But if I wanted to find out my displacement from where I started, so let's say I started here, my displacement is this vector here, straight to the library. So what you're going to learn in part today is how I would take the numbers for each of these 2 vectors and put them together, even if they don't form a right triangle. So you're going to learn how to do this even when it's not a right triangle. Alright, so first thing we need to learn is that we can take vectors and resolve them into a perpendicular components using a 2-dimensional coordinate system. And I'll show you what that means. It could be confusing. Suppose you have a vector, let's look at part A here. Suppose you have a vector that's 1.5 meters long at an angle of 25 degrees with respect to the origin. Okay, now if you're wondering, well, how would you know 25 degrees? You can set up your own coordinate system. So I could set up a coordinate system around that vector that might have a different angle, and I'll get the same answers. Okay, so I have a vector 1.5 meters long at an angle of 25 degrees with respect to the origin, with respect to the x-axis. Now I want to break up that vector into its x and y parts. So let's say this was my displacement vector. I want to know how far the person went north along y and how far the person went east along x, and I can break that vector into those parts. The way I do that is with trig functions. The vertical part of a vector, when the angle is with respect to the x-axis, so notice here my angle is from the x-axis to the vector, when that's the case, the vertical component is the sine part of that vector, and the horizontal component is the cosine. So we're going to use trig functions to resolve, and resolve means break the vector up into parts, so you can use trig functions to resolve the vector components. So now over on the right side in part B, this is where I've broken the vector up into its parts. So let me show you how I got both of these numbers. Rx, or the horizontal x component right here, I got by taking the length of the vector, 1.5 meters, and multiplying it by the cosine of the angle between the vector and the x-axis, 25 degrees. So 1.5 meters cosine 25 degrees. For the purposes of resolving vector components, degrees are fine. You don't need to use radians at this point. And if you don't know what that means, it's okay. If you do know what that means, stick with degrees for now. All right, and to get the y component, so our y, I did 1.50 meters, or the length of the vector, times the sine of the angle between the vector and the x-axis. So the vertical part is sine, the horizontal part is cosine. And at this point you would just do the sine and cosine with the calculator if you're wondering about that. So 1.5 sine 25 degrees, 1.5 cosine 25 degrees in the calculator. Let's say we have a vector pointing to the right and down. When we resolve that vector into its components, the x part will point to the right, which is generally considered the positive x-axis. And so up at the top above that graph you can see ax is greater than 0, so that component would be positive. And the y component would point downward, which is generally considered down on the y-axis is generally considered negative. And you can see up at the top again, ay is less than 0 or negative. Alright, now let's say we had a vector, example B, that points down and to the left. Ax would be less than 0. It would be pointing to the left, which is generally negative on the x-axis. It's negative. Oh, I need to switch colors to avoid confusion. So that's pointing to the left, generally negative on the x-axis. And the y component would be pointing downward, which is also generally negative. And you can see ay less than 0. Now, example C. Let's say we have a vector pointing up and to the left. When we resolve it into its components, the y component will be pointing up, which is generally positive. The x component will be pointing left, which is generally negative. So you can think about these as being at the origin of an xy axis, and then you just use whether the way it points in a coordinate system would be positive or negative. So down on y is negative, up on y is positive, right on x is positive, left on x is negative. And so you can just use those rules. If you have one down and to the left, you just combine them. Down y negative, left x negative. Up and to the right, up at y positive, right x positive. And final example is, in fact, up and to the right. It has a component up, which on a y-axis would be positive, and it has a component to the right, which on an x-axis would also be positive. Right. If you got confused, maybe watch that one more time. I did go pretty fast. And try a few on your own. Maybe rewatch the video, pause it before I do each one, and say which one should this be. Be a great way to practice it. Alright, now we're going to take some vectors and divide them into their component parts. So this would be an example you might want to do on the back, or since it's on the grid paper, on the front. Maybe watch the example and then decide where to draw it. Just use your best judgment, because I am going to use the fact it's on a grid. Okay, so first I'm going to define a coordinate system and put the vector at the origin of that coordinate system. Oh, at the origin. So we've got an x part and we've got a y part. Okay, since I'm fortunate enough that this vector was drawn on grid paper, all I have to do is count. And so first, let's find the horizontal x component. Notice I can break this vector up into up and to the right. Take a second and guess what the signs of each of those component vectors will be. I said up and to the right. Right, now I'll just count the boxes to get the horizontal component. So notice I don't have to do trig here. Don't have to find the sine or cosine because it was drawn on grid paper. Alright, so x boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So my horizontal component is 14, and since I don't know what these boxes represent, 14 boxes. And since that's to the right, it should be, take a guess, positive. And now, count my vertical component. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My vertical component is 10 boxes, and that was up, so it is positive. Notice, all I'm doing is taking the vector and making a right triangle and figuring out the length of each of its sides. So take a vector, make a right triangle, figure out the length of its sides. That's the basic steps to resolving a vector into components. Okay, you try this one. The hint I will give you: first, define a coordinate system with the vector at the origin. That makes it easier to determine the signs, positive and negative. Do this one, pause the video. Once you've done it, come back for the answer. Alright, here's what I got. I counted for the vertical or up and down component and got -9 boxes. Negative because it's down, and on the y-axis, down is negative. Hence why I had to define the coordinate system. And 11 boxes for the horizontal component, and that's positive because it's to the right. And on a Cartesian coordinate system, right is usually positive. So positive 11 boxes for the horizontal component. Alright, so let's do this vector as an example. I'm going to divide it up into its horizontal and vertical components. And this time I will have to use trig to do that. So I notice that this vector has a magnitude of 5 meters per second and a length of and an angle of 30 degrees with respect to the x-axis. So, to find its horizontal or x component, and I'm just going to call it Rx for convenience, that would be 5 meters per second times the cosine of 30 degrees. And if I grab a calculator and do that, 5 cosine 30 degrees, I get 4.33, and this will keep the same units as the vector itself, meters, or as the original vector, meters per second. And then to do the y, or vertical component, Ry, is 5 meters per second times the sine of 30 degrees. If I do 5 sine 30 degrees, I get 2.5, and it keeps the units meters per second. Okay. So our horizontal component, to answer the question that's written up at the top, is 4.33 meters per second, and the vertical component is 2.5 meters per second. And I hope it didn't confuse anybody that this 5 went with the original vector. Oh, and now we have to pick positive and negative. So Rx is to the right, which would make it positive, and Ry is pointing up, which would also make it positive. Okay, I want you to try this on your own, and I'm realizing some of my numbers have disappeared. So, this is going to be 50 degrees, and you're just going to use the variable v for the length of the vector. So your answer is going to be in terms of v. Try this one. It is tricky because it doesn't have a number. Try it, pause the video, come back when you're ready for the answer. Okay, so this one might have even been too tricky to have you try on your own. What makes this one super tricky is notice that the angle is actually opposite Rx. So in terms of trig, the opposite line is Rx and the adjacent line is Ry. So you actually can't use sine and cosine in the same way in this one. So here, Rx, because it is opposite, and remember SOHCAHTOA, sine opposite hypotenuse. And so since Rx is opposite the angle, I would actually use the sine to get this one. So the answer will be Rx is V sine 50 degrees. And Ry here is adjacent to the angle, adjacent, so ka-toa, cosine adjacent hypotenuse. And I'll get V cosine 50 degrees. So that's tricky. Generally, x will be cosine and y will be sine, but you do have to pay attention to where the x and y are in relation to whatever angle you're given. So if we were given this angle here, instead we could use cosine for x because it's adjacent, and sine for y because it's opposite. So you do have to pay attention to where they are. In this case, x was opposite, so ka-toa, sine, opposite, and y was adjacent, so cosine, cosine adjacent to the hypotenuse. Alright, there we go. If you need to rewatch that section again, it's understandable. It can be confusing because you just learned of a case where sine and cosine work differently than the first few examples I gave you. Now let's talk about how we add vectors. So suppose you had treasure buried somewhere, and your treasure map said start at the sycamore tree, which is on this map. Start at the sycamore tree, go 5 paces north, 3 paces east, and 4 paces southeast. Well, you could do all that, or you could go straight to the treasure by finding the vector that leads you straight to the treasure. And the way you find that vector is by adding the other vectors together. And there we go. How to add vectors is by placing each vector tip to tail. So notice one tip, which is the part with the arrow, and one tail, the part without the arrow, meet here. Another tip and tail, part with an arrow, part without an arrow, meet there. Tip to tail. And it doesn't matter what order you do this in. Any order you had arranged those vectors, you would still get to the same place. You can also add vectors using math instead of doing it visually. Here are the 3 steps to adding vectors using components. So first, find the components of each vector to be added. This is what I've been calling resolving. So resolve the vectors into their components. Add the x and y separately. So let's say you get 2 Rx's, Rx1, Rx2. Those will give you your total Rx. And then Ry1, I don't know why I'm capitalizing the second one, Ry2 gives you your total Ry. And then you put those 2 together, which I'll show you how to do in a second. So that's how you add vectors using math. The last slide was how to add vectors graphically by drawing them. Okay, so I'm going to take these 2 vectors and let's add them both mathematically and visually. So first, visually. I'm going to take the red vector and put its tail at the tip of the blue vector. And I could do it with the blue vector. I could take the blue vector and put its tail at the tip of the red vector. But let's do this. So I'm going to draw these, and first I need to figure out how the red vector is drawn on the grid. So I see that it takes up 1, 2, 3, 4, 5 places vertically, 1, 2, 3 places horizontally. So when I draw it over here, I want to start at the tip of the blue vector and have gone 1, 2, 3, 4, 5 vertically, and 1, 2, 3 horizontally, tail to tip. Okay? And then my resultant vector goes from the tail of the first vector to the tip of the second vector. Or if you had more than one, tail of the first to tip of the last. So the purple vector here, that is my resultant vector. Now let's try to do this mathematically. So I need to resolve both vectors into their component parts. And I've already done that with the red vector. Horizontally, it had 3 boxes, and those were to the right, so that's positive. Vertically, the red vector had 5 boxes. I'm just going to go ahead and abbreviate box B. And those were down, so that's negative. So Ry, negative 5 boxes, Rx for the red vector, positive 3 boxes. Now let's do it for the blue vector. It has vertically 1, 2, 3, 4, 5 boxes. and those are up, so those are positive, and that's ry, vertical. And then horizontally it has 1, 2, 3, 4, 5, 6, 7 boxes. And those are to the right, so those are also positive. And by the way, that was Rx for that one. So now I want to add them together. My total Rx, x total, is positive 3 boxes plus positive 7 boxes, and my Ry total is negative 5 boxes from the red vector and positive 5 boxes from the blue vector. And then if I just add those together, so Rx total equals 10 boxes, Ry total equals 0 boxes. And in this case, since I know Ry goes away, this is 0 boxes, I don't have to worry about it. And my total vector in the end, so just R total, the purple vector, is 10 boxes. And it is to the right, or in the positive x, so positive 10 boxes. And I'm just going to go ahead and give it its direction to the right. Okay. Alright, try this set of vectors on your own. Add them both visually and mathematically, and then come back for the correct answer. So pause the video, try them, come back for the right answer. Alright, so you probably got stuck on this one, which is good. So I imagine you could get this far and find that the total Rx is 13 boxes, total Ry is negative 10 boxes. But then you weren't sure how to find the final vector. So let's do that. You will always use the Pythagorean theorem, even when your final vector doesn't look like a right triangle. Trust me, it does, because we could divide this up into a y and an x. So all you do is the final vector squared is Rx squared plus Ry squared. Okay? And then whatever you get there, you take the square root. So R equals square root Rx squared plus Ry squared. So let's do that with those numbers. If I take Rx, which is 13 boxes, square that, plus Ry, which is negative 10 boxes, square that, and you're also squaring the negative, so it becomes positive. We get 269, square root of that is 16.4. So R is 16.4 boxes long. And now, you might be wondering, well, is the final vector positive or negative? It doesn't quite work like that. Now we have to find the angle for the final vector. And to find the angle, you're going to use an inverse tangent. So the angle between the vectors is always the inverse tangent of Ry over Rx. And I think your book does this with the letter C, Cy and Cx. For the purposes now, know that tangent is opposite over adjacent. So we're finding the ratio of Ry to Rx, and then figuring out what the angle must be using tangent. That's something for your pre-cal teacher to really cover in depth, the meaning of tangent. And so I'll save that for them, because most of you are in pre-cal or have had pre-cal. If it gets to the point where you just can't handle doing this without knowing what tangent means on a deep level, we can do that together. But for now, know that the angle between them you use by finding the inverse tangent function of the calculator. So tangent -1, which is actually a button on your calculators that you have in class. And tomorrow I can show you that on ours. tangent negative 1, and then your values for rx and ry. In this case, 13b over negative 10b. So in my calculator, I'm going to hit the tangent negative 1 button, 13 over negative 10. My calculator tells me that the angle between those two vectors is negative 52.4 degrees. And so the final vector r, we're going to bring that angle in with it, is 16.4 boxes at an angle of negative 52.4 degrees. You can use the word at, you can use the symbol at. I've never met anybody that actually cares. 16.4 boxes at an angle of negative 52.4 degrees. Mr. Melvin, why did you give us an example this hard to try on our own? Because I wanted you to get stuck. If you're confused about what I did, look at page 64 where it says adding vectors using components. They walk you through everything I just did, except they call it cx and cy instead of rx and ry. So adding vectors using components on page 64 that goes over to page 65 is what I just did. So now let's talk about how to subtract vectors. I'm not going to spend much time on this because it's super simple. When you subtract a vector, let's say we were going to do vector A on this chart, vector A minus vector B. And I'm going to use vector notation on this slide. You'll see what I mean in a second. Vector A minus vector B. The way you would write that, vector D, as they've called it on this slide, is vector A minus vector B. And those little harpoons that I'm drawing over the letters, and then they're drawn on the slide, like right here and right here, those little harpoons just mean the thing is a vector. So it's not just a number, it's a vector, and that's what those indicate. We'll use that more later on as we need it. To do this visually, all I do is I take vector B and I flip it around the other way, and then put the flipped vector's tail at the tip of A. So you change its direction. There you go. Notice how it just flipped. Now, to find mathematically what vector D would be, we're going to divide it into components. Let me do this along the side here. The x component of D is the x component of A minus the x component of B. The y component of D is the y component of A minus the y component of B. And then you'd use the Pythagorean theorem and tangent to find D. Okay, so we'd add ax minus bx, ay minus by. We'd have to say that d squared is dx squared plus dy squared. And then we would find the angle between the two, tangent negative 1 dy over dx. And tangent is y over x. And offhand, I can't think of an example where that would get reversed. So again, if you need help with that, there is then a section starting on page 65, subtracting vectors, and going on to page 66 that does everything I just did laid out on a page. So if you need help with that, you can look at those pages. All right, that's it for tonight's video. See you tomorrow.